Alright, time for another draftphysics.com, debatephysics.com, also video presentation. So, I have to eat a little crow, I guess. You know, should never be too confident. It's always dangerous. Anyway, so the drag simulation has revealed something I didn't anticipate, and basically is demonstrating that yes, drag is still a thing. And my simple description of why it wouldn't be a thing is too simple. Yeah, just a little short. So there are other things to consider. I'll probably still play with it, but the point is that yes, it does. The simulation does demonstrate that yes, there is drag. So I will add one bit from the other side. There it is, the orange thing, and you can see it does exactly what I anticipated until it doesn't. Yeah, exactly. So it'll move probably, it should move actually to that line. Yeah, it's just about there, a little closer. Come on, you can do it. Um, and yes, it does happen. So it does exactly what I anticipate, and then it goes and then it stops and it goes and it stops and it goes and stops. The problem is what's happening is the distance from the emitters is changing. So as you move something, you're getting it closer to one emitter and further away from the other. And that itself doesn't mean anything, but it's sort of the same thing as blue shifting and red shifting. In the sense, right at the object, you're red shifting or blue shifting, and what you're really doing is adding space. So on this side, the side it moved away from, it added some corral space. If I use my buffalo analogy, now the buffaloes can stay in that space because I just created more space on this side so buffaloes can sit in it. And so instead of hitting me, they're still in that space. And on the other side, I made the corral smaller, which means there's no room for the extra buffaloes, so they had to hit me. So the only way, so I've basically guaranteed that I get hit by a couple of extra buffaloes from the one side and the other side. In this case, just one. And the distance is always relative. So if I wanted to go twice the distance, I could just hit this button twice and send two bits in, and then it'll move twice the distance. And the distance really just represents how far apart those little dots are. So if I pause this in a second, let it go all the way. So it's very proportional. As you can see, it works perfectly. Twice the amount of fuel, twice the distance, but it does stop right on the line. It's just a coincidence. But anyway, so if I pause it, you can see there's 3 bits here and 2 bits and probably a third one there. If I divided that space by 3, the space would be a half division. And you're really just saying as soon as you have a half division of space from each side, then it stops moving because you've basically created more space on one side than the other side. So it does still drag to a halt, which from my perspective is disappointing, but it's science and the truth matters and all that kind of stuff. And so we're back to the fact that we sort of know things aren't dragged very much, and we know the speed of light is, this is a relative. This motion is not that much different than the motion of the force, and obviously if we change these proportions, it will drag less, but the point is it is dragging. So, we just know that objects don't drag, and we know that electrons and protons do drag. So there's lots of facts to still play with, indicating it's not an open and shut kind of thing. It's just finding exactly what the mechanism, in the real universe is. And but clearly, distance from sources matters, and the further you go away from a source, essentially, like I said, it's essentially red shifting, at least for the time you're moving. So the time you're moving, you're red shifting, and you're going to get less energy because you're widen the space the energy has to go through. And so it can't get to you because you've widened the space it has to travel, essentially. So, yeah, so back to the drawing board in some sense. So there's two versions of this, links below. So this is the version where as it moves, it gets closer and further away from sources. The other version, the sources move with the object, and as I would have predicted, as I was thinking, you can't change how much force is hitting something, but you obviously can. Yeah, it works fine. You know, there's no drag. As long as the source is the same distance from the object, no drag. So, you know, still some thinking to do, but on the surface, yes, no, my recent explanation isn't good enough, and the simulation demonstrates it. So that's the value of the simulation. It also demonstrated a lot of other curiosities, and so on the redshift argument, it basically demonstrates if I redshift from the source, then it matters how long the distance is, because the redshifting won't be able to get to the object for perhaps 1 billion years. So if a planet moves away from us all of a sudden, our sun, 1 billion light years away, it'll take 1 billion years for us to see the redshift. But if I move the target, it happens right at the target. There's no, the signal, the fact that I've redshifted isn't noticed by the source. The source has no idea I moved the target. And that makes intuitive sense that how could it possibly know? But it also demonstrates that widening the distance isn't reversible. It really matters whether you move this object or you move this object. If you move the source, it's different than if you move the target. And that's an interesting fact gleaned out of this. And such. So that's the bright side is, you know, there's something to learn. You know, so you can adjust the speed and all that kind of stuff. You know, I'm not terribly interested now because I already know it doesn't work, so it doesn't really matter. You know, it's all really a nice little simulation. So at least if you want a demonstration of drag being real, this simulation will do it. Again, the other version is basically it's not a cheat, but it's you know, it creates a universe where the force is constant, and I just don't think the real universe, the force can possibly be constant because you are moving. Now, there's a whole bunch of other stuff to consider, so, well, maybe I'll do some of that. So it's not, the subject isn't over yet, but at least in this form, it's not over yet, just because there are elements that matter. So you could think of the source as an infinite plane. So like one side of the universe is producing, you know, lots of little stuff in all kinds of directions. So there's stuff moving this way, there's stuff doing that, there's all this, and it's like an infinite plane. And so if there's an infinite plane, the fact is no matter where you are, the same light hits you is the sort of the argument. So it's like being in a hollowed out center of the earth. There wouldn't be any gravity in any one location. You couldn't be pushed anywhere. And, you know, but the argument is in that circumstance, would you keep moving? Is there drag inside the center of the earth if you could live inside of it? And I guess that's the part where I'm saying it's sort of an open question, because you can sort of understand that what happens is as you get further away from a target, you get smaller, okay, as a target. And as you get closer, you get bigger. So if you were to, you know, draw an object, it's getting bigger as it moves towards one source, and it's getting smaller as it moves from the other light source. And so that's the reason why it always ends up balanced, even though you can see more of the infinite plane this way than you can see from this angle. So, you know, but the trick is that I can take that same diagram and think of it as a more realistic in terms of understanding the universe as a sphere or something, and what you're being affected by when you move in the universe is there's stuff above you, there's stuff left of you, there's stuff in all these positions. And when you're moving, say, from this center point to this line, you can sort of understand that you're exposed to a much smaller universe on this side hitting you than the universe on this side. Okay. And these lines, okay, unlike this, see, this has a huge change in the length of the line. This line only changes a little tiny bit, and this line changes a little less. It's not as much of a change. So you can make sort of the argument that all the force hitting you from these other angles don't have the same amount of space they're creating. And again, you have to do this, your object's getting smaller and this object's got bigger, so even though there's smaller sources, fewer sources hitting this object, the object itself is bigger. And part of when you're moving, what you're doing is you're going from a point where you were here, and so there's a place where this energy was hitting you going that way, but when you're over here, that energy was hitting you this way, okay, and that's not hitting you anymore, and now it's reversed. So you basically took stuff that was on this side, moved it to this side. It's like the guns are now pointing at you that before were pushing you one way. Now the gun's pushing the opposite way. So that's a sort of intriguing possibility that's what compensates. But that's going to be a much more complicated simulation, obviously. And so that'll be on a back burner. Because that's going to, much more elaborate. And then especially when you think of it in 3 dimensions, and, it gets a little bit too complicated to be practical at this time. So anyway, the bottom line is I spoke a little too soon with a little too much confidence, and just a fact. And regrettably, I can't say that I've solved the drag problem. Like I stated, I have some positive threads of reasoning, but nothing sewn. Yeah, so I thought this was going to sew it up, but it didn't. And just a fact. And it's disappointing, but let's throw one from the other side just for the fun of it. And so, like I said, it really does exactly what I anticipated, until it doesn't, which is irritating and such. But perfectly understandable that I should have seen the defect, and I didn't, and just the way it is. So, next simulation will be the gravity one, so I'm fairly confident that one will work out. So, you win some, you lose some, blah, blah, blah. But anyway, so yes, drag is still a subject, unfortunately. And so just thought I'd make a video pointing that out. And so thanks to Daniel, yeah, am I going to say the name right? Berleman. Pretty close. Anyway, he's the one who did the simulation. I've been off and on talking to him for a number of years, and he was sort of he realized first the idea of the electron force going into a proton and coming out proton force as a mechanism, a possible mechanism. And I rejected the idea on its face for whatever reason at the time. And then later, I, without, remembering that that's what he had stated, I ended up creating the same mechanism. And in hindsight, yes, it was, it's just a matter of how you get somewhere. It makes sense. So if you come at some things from one angle, it doesn't make any sense. But if you come at it from another angle, then all of a sudden it makes perfectly good sense. But anyway, so I drew the same conclusion. And so anyway, I'm just giving him credit where credit's due. He has been very useful in being, providing feedback and these kind of mechanisms. He hasn't really had the time to devote to making simulations, but he's made this one. So maybe we'll get a few. And so anyway, just can't really say how helpful the couple of people who have helped me with the simulations are just a huge benefit in reasoning, because you have to think about how to build the simulation, and in thinking about building the simulation you think about how things function and how to do it as simple as possible and all that kind of stuff, and all of that reveals truths that you didn't realize, as this simulation did. So anyway, enough of a video, I guess. Keep it simple and such. So the other simulation will eventually be the double slit experiment, and demonstrating that it's just about action on the surfaces, and it doesn't have anything to do with creating waves or altering waves or anything to do with waves. Photons are made of particles. All right, so and this sort of, again, the simulation is sort of useful for that, because if I did send these at a very consistent frequency, you would actually see that right here it's being red shifted, and here it's being blue shifted, basically because of that motion. For the time you're moving, you're causing a blue shift in that direction and a red shift in that direction. So it's and the reflections reveal that, and so there's again, there's tangential value in simulating one thing, and it shows you some insight into something else, which is also valuable. All right, so enough. Yeah, disappointed, but you have to just endeavor to persevere, and so that's what I'll do. And it'll just be a reminder, don't get too confident, something before the fall kind of thing. Yeah, don't do that something before the fall. So anyway, till the next time, and such and so forth.